Module 14, DNP3 in Modern Utility Ecosystems, Coexistence, Integration, and Future-Proof Operation. 14.1, Within Heterogeneous Utility Environments. Modern utility ecosystems are multi-protocol, multi-generation, and multi-domain by necessity. No single protocol operates in isolation. DNP3 exists alongside protection protocols, substation automation frameworks, enterprise data systems, and analytics platforms. DNP3's continued relevance stems from its ability to coexist without conflict, maintaining a clearly defined operational boundary while integrating into broader system architectures. Number 14.2, Separation of Operational and Enterprise Domains. Operational Technology, OT domain. Within the OT domain, DNP3 is responsible for deterministic data acquisition, explicit control execution, event reporting with temporal integrity, safe interaction with physical assets. This domain prioritizes predictability, safety, and correctness. Information Technology IT domain, enterprise systems focus on data aggregation and analytics, asset management, planning and optimization, market and regulatory reporting. DNP3 does not attempt to operate in this domain directly. Boundary discipline DNP3 acts as a clean interface between OT and IT. OT systems produce authoritative operational data. IT systems consume, transform, and analyze that data. This separation prevents enterprise complexity from destabilizing field operations. 14.3, Integration through data abstraction layers. Protocol gateways and data brokers. Integration between DNP3 and higher-level systems typically occurs through data concentrators, protocol gateways, middleware platforms. These components translate DNP3 objects into enterprise-friendly representations without altering field behavior. Preservation of semantics. Critical integration principle. Open quote, DNP3 semantics must be preserved across abstraction layers. Close quote, flags, timestamps, and quality indicators must remain intact to prevent misinterpretation at higher levels. And 14.4, Coexistence with other utility protocols, parallel protocol operation. DNP3 commonly operates alongside protection-focused protocols, substation configuration protocols, time synchronization protocols. Each protocol serves a distinct purpose. Avoidance of functional overlap. DNP3 deliberately avoids high-speed protection messaging, self-describing object models, automated device discovery. This restraint prevents competition for responsibilities and preserves clarity. Number 14.5, Interoperability at the architectural level. Architectural interoperability versus protocol interoperability. While protocol interoperability ensures devices can communicate, architectural interoperability ensures systems can coexist meaningfully. DNP3 supports architectural interoperability by maintaining stable semantics, enforcing explicit behavior, avoiding hidden state. This allows system designers to reason about behavior across domains. 14.6, DNP3 as a stable anchor in hybrid systems. Legacy meets modern infrastructure. Utility environments often combine legacy RTUs and serial links, modern IEDs and Ethernet networks. Centralized cloud-based analytics, DNP3 functions as a stable anchor, bridging generations without forcing convergence. Incremental modernization utilities can modernize by replacing communication media, adding analytics layers, introducing automation logic while keeping DNP3 field interfaces unchanged. And 4.7, Data Ownership and Authority. Authoritative source principle. In DNP3-based systems, outstations are authoritative for field data. Masters are authoritative for control decisions. Higher-level systems must treat DNP3 data as ground truth, not estimates. Enterprise systems should not directly influence DNP3 control paths without explicit validation, human oversight, deterministic control logic. This prevents unintended feedback loops. NAT 14.8, Scaling across organizational boundaries. Multi-control center environments. Large utilities may operate multiple control centers, regional operation zones, shared infrastructure. DNP3 supports this through logical addressing, hierarchical architectures, controlled master-outstation relationships. Clear ownership prevents command contention. 14.9, Analytics and digital twins. Data consumption without control. Coupling modern analytics platforms and digital twins consume DNP3 data to model system behavior, predict failures, optimize operations. These systems must remain observational, not authoritative. Preservation of real-time determinism. Analytics operate asynchronously and must not impose timing constraints on DNP3 communication cycles. 14.10 Cloud and Remote Access Considerations. Controlled exposure. When DNP3 data is exposed beyond traditional boundaries, access must be mediated, control paths must remain isolated, latency and reliability assumptions must be preserved. DNP3 itself remains unchanged. Exposure is managed externally. Morph 11 Avoidance Protocol Dilution. Risks of overextension, attempts to extend DNP3 to cover, bulk data transfer, high-level orchestration, autonomous decision-making risk diluting its core strengths. Discipline of scope. DNP3 remains effective precisely because it refuses to expand beyond its purpose. ASH. 14.12 Human Oversight in Integrated Systems. Operator-in-the-loop principle. Regardless of integration level, humans remain responsible for control decisions, automation remains bounded and auditable. DNP3's explicit semantics support this principle. 14-point term coexistence strategy. DNP3's future relevance depends on stable semantics, strict backward compatibility, respect for architectural boundaries. As long as utilities value deterministic control and operational clarity, DNP3 retains its role. Number 14.14 Summary. DNP3 as an ecosystem-compatible protocol. DNP3 thrives not by dominating the utility ecosystem, but by fitting into it precisely. Its enduring strengths are clear operational boundaries, semantic stability, deterministic behavior, integration-friendly design. In increasingly complex utility environments, DNP3 continues to serve as a reliable, disciplined, and trustworthy operational core, coexisting with modern systems without being destabilized by them. Module 15. DNP3 as a systems engineering discipline. Design intent, operational rigor, and failure-aware thinking. Number 15.1. DNP3 as more than a protocol. By the time a utility system reaches full operational maturity, DNP3 is no longer experienced merely as a protocol specification. It becomes a systems engineering discipline, a way of thinking about communication, control, failure, and responsibility in environments where software actions have physical consequences. DNP3 embeds engineering assumptions about how systems should fail, how uncertainty should be expressed, how authority should be exercised, how recovery should occur. These assumptions shape not just code, but organizational behavior. Now 15.2, Engineering for Failure, not for perfection. Failure as a normal operating condition. DNP3 is designed with the assumption that links will fail, devices will reboot, data will arrive late or not at all, commands will occasionally be rejected. Failure is not exceptional, it is expected. Explicit failure modeling. Rather than masking failure, DNP3 exposes it through explicit error responses, quality flags, timeouts and retries, deterministic rejection behavior. This allows engineers and operators to reason about what failed, where, and why. Number 15.3, Bounded responsibility and authority. Clear ownership of decisions. DNP3 enforces strict boundaries. Outstations report, state, and execute commands. Masters decide what to command and when. The protocol does not arbitrate intent. This prevents diffusion of responsibility across layers. No implicit escalation of authority. A device cannot assume control without being addressed, execute actions without explicit commands, modify its role dynamically. Authority is always conferred, never inferred. Hashtag 15.4 Discipline of explicitness. Nothing happens implicitly in DNP3. Reads do not cause writes. Events do not imply commands. Connectivity does not imply permission. Every meaningful action requires an explicit request and an explicit response. Engineering consequence. This explicitness increases verbosity, reduces ambiguity, eliminates hidden coupling. Systems become easier to test, audit, and reason about. Tashta 15.5 Designing for recoverability. Recovery as a first-class requirement. DNP3 systems are designed to recover cleanly from interruption. Recovery mechanisms include event buffering, integrity polling, deterministic resynchronization, time realignment. Recovery does not depend on operator intuition or undocumented behavior. Predictable recovery sequences. After a fault, recovery follows known steps. 1. Communication reestablishment. 2. Event buffer draining. 3. State reconciliation. 4. Time synchronization. Predictability is more valuable than speed. 15.6 Avoidance of emergent behavior. Resistance to complex interaction effects. DNP3 avoids features that could cause implicit state machines, dynamic negotiation of semantics, self-modifying behavior. As a result, system behavior does not emerge unpredictably under stress. Systems remain explainable. Every observed behavior can be traced back to a specific request, a defined response, a documented rule. Explainability is essential in post-event analysis. 15.7 Alignment with safety-critical engineering principles. Conservative by design. DNP3 aligns with safety-critical engineering traditions. Prefer rejection over unsafe execution. Prefer explicit failure over silent success. Prefer stability over optimization. This conservatism is intentional, not accidental. Minimization of surprise. Surprising behavior is treated as a defect, not a feature. The protocol is designed so that operators are not startled by system responses, engineers are not surprised by edge cases. Now to 15.8 Human factors embedded in the protocol. Support for operator mental models. DNP3 interactions mirror human workflows. Ask, receive, select, confirm, operate, observe, decide, act. This reduces cognitive translation between system behavior and human intent. Stress-resilient operation. During abnormal conditions, operators rely on predictable responses, clear rejection messages, stable system behavior. DNP3 is engineered to remain intelligible under pressure. Number 15.9 Organizational effects of deterministic protocols. Reduction of tribal knowledge. Because behavior is explicit and standardized, fewer undocumented assumptions exist. Knowledge is encoded in configuration, not memory. Training becomes transferable. This improves resilience to staff turnover. Repeatable engineering practices DNP3 enables standardized testing, reusable system designs, consistent operational procedures. Engineering effort compounds rather than resets. 15.10 Change as a controlled process. Resistance to casual modification. DNP3 systems discourage ad hoc changes, unreviewed configuration edits, quick fixes in live environments. Because effects are explicit, changes are visible and therefore accountable. Predictable impact analysis engineers can analyze changes by asking which points are affected, which functions are impacted, which recovery paths are altered. This supports disciplined change management. 15.11 Limits as a strength. Intentional constraints. DNP3 deliberately does not attempt to automate decision-making, abstract physical processes, optimize for convenience. These limits preserve clarity and prevent overreach. Stability through restraint. The protocol's refusal to expand beyond its purpose is a key reason it remains stable across decades. At 15.12, DNP3 as an engineering culture artifact. Over time, DNP3 shapes how organizations think about systems. Explicitness over cleverness, determinism over adaptability, safety over speed. The protocol encodes values as much as it encodes data. 15.13 Why DNP3 survives technological cycles. Technologies rise and fall, but DNP3 persists because physical systems still require deterministic control, human accountability still matters, failure still needs to be understood, not hidden. These needs do not change with technology trends. 15. Final synthesis. DNP3 as disciplined engineering. DNP3 endures because it treats communication as a serious engineering problem, not a convenience layer. It succeeds by insisting that every action be explicit, every failure be visible, every recovery be deterministic. In critical infrastructure, where ambiguity translates directly into risk, this discipline is not optional. It is the reason DNP3 continues to function as a reliable foundation long after newer technologies have come and gone.